Welcome back, everyone. In this video, I will begin going over the lecture for indeterminate forms. And the main thing in this section is something called L'Hôpital's rule, or it sort of looks like the hospital's rule. You can pronounce it either way you want. Just know, sort of like L'Hôpital's, the hospital's rule, whichever one you call it, that's going to be a rule for evaluating limits that makes a lot of limits that we had trouble with or we would not have been able to do before a lot easier. And they're all based around indeterminate forms. So I want to start this section off by looking at all the indeterminate forms. Then we'll look at L'Hôpital's rule, and then I'll come back to this and kind of talk about why I have the indeterminate forms separated like this. All right, so when we started doing limits, pretty much from the very first section, when we talked about limit laws, we had some indeterminate forms, 0 over 0. And we saw examples where the limit, when you plug in the number, you get 0 over 0, but that didn't tell us what the answer was because it could still have been infinity. The limit could still have been 0, but it could also have been any number at all. Well, we actually have seen a couple of these already when we did limits at infinity. So these right here are all the indeterminate forms we need for this class. And if I remember correctly, these are actually all the indeterminate forms anyway. So all the indeterminate forms are based around having 0, infinity, or 1 somewhere. And they all come from basically if you can rearrange something to make it look like 0 over 0. Infinity over infinity was kind of one of the base ones as well, so we won't really be rearranging infinity over infinity when we do problems. But something like 0 times infinity, something like infinity minus infinity, something like 0 to the 0 power, infinity to the 0 power, or 1 to the infinity power are all things that if you do some algebraic manipulation, you can actually make them all exactly 0 over 0 or infinity over infinity. Now, as we go through the problems, we'll see that the strategy for doing that when you work the problems is all the same in the category. So when you have a 0 times infinity, you're always going to do the same sort of thing. When you have an infinity minus infinity, you'll always do that same sort of thing. When you have one of these exponents, it doesn't matter which one it is, you'll always do the same sort of thing. So if I show you how to do a problem with 0 to the 0, and you're asked to do a problem with 1 to the infinity, you just follow the same exact strategy. And I'll kind of reveal those strategies as we go through the problems, and then I'll just write them in up here once we've actually worked through one. All right, so L'Hôpital's rule states the following. It says if the limit as x goes to a of a fraction f of x over g of x equals 0 over 0, or the limit as x goes to a of f of x over g of x equals plus or minus infinity over infinity. Now this plus or minus, you see I have it drawn on here for the indeterminate form. It doesn't matter whether it's infinity over infinity or negative infinity over infinity, so that's why the plus or minus is there. A lot of people just refer to this indeterminate form as infinity over infinity, but I wanted to make it clear that if you have a negative there, it's still valid. And another quick thing I want to add is that when we're looking at these, when we have our base ones, so when we're doing a limit of a fraction and we get 0 or 0 or infinity over infinity, it's pretty much saying that the limit of the top is 0, the limit of the bottom is 0, or in this form, the limit of the top is infinity, the limit of the bottom is infinity as well. When we have some of these, we're just gonna, how we always evaluate limits is we plug them in. And then if we end up getting one of these forms here, it's called an indeterminate form, and we'll have to do something to it to make it look like one of these. Right? But what L'Hôpital's rule says is the following. So if you get one of these two fraction forms of indeterminate form, 0 over 0 or infinity over infinity, then what you're allowed to do, and it's valid, is that the limit as x goes to a of f of x over g of x, so the limit what you're trying to do, well, it doesn't give you the answer, but it tells you what to do. It tells you take the limit as x goes to a, but do the derivative of the top and do the derivative of the bottom. All right, now one thing that's very important about this rule that's a little hard to just grasp is that we have a derivative rule for fractions called the quotient rule. This has nothing to do with the quotient rule. This is just saying if you have a fraction and when you plug in to do the limit and you get one of these two forms, then to help yourself figure it out, you can do the derivative of the top by itself and the derivative of the bottom by itself. So one thing I really emphasize here is it's not the quotient rule. You do the top separately, the bottom separately, right? And one thing is that you can do it once. So let's say you do the derivative of the top and the derivative of the bottom, and you plug in your number because that's what we do after we do any sort of limit rules, which this is one of our limit rules. We plug in the number and see if it works. If you still get it 0 over 0 or infinity, you can just keep on doing it until it's not an indeterminate form. Right? And it also works for one-sided limits. So if you see any problems in this section, if you go back and look at any one-sided limit problems, you can also use L'Hopital's rule for that. Right, now the main thing to really reinforce, and I kind of mentioned it already, is that L'Hopital's rule only works for these two special forms. So if you're in a different indeterminate form, you must convert it to 0 over 0 or infinity over infinity. Doesn't matter if it's positive or negative, you must convert it. So like I was saying, if you're in any of these three forms, we have 5 different possibilities. You have to convert it. And then also, if you're not in an indeterminate form at all, so if you just plug in your x equals a and you get something that's not one of your, I guess we have 7 indeterminate forms if you look at them up here, then you're already done because that means you have a number for your limit that's not indeterminate, and that is your answer. And what you don't want to do is forget all those limit rules that we talked about before. So we had quite a bit before, and we pretty much developed a strategy to doing any limit, which was plug in the number. If we got 0 over 0 or infinity over infinity, because that's really what we had back then we had to algebraically manipulate or do something to solve the problem. Now we're just going to have L'Hopital's rule that really just lets us do it all at once. One thing that's kind of useful just to remember is that if you have any of those old problems, you think back to when we were doing limits at infinity of rational functions, something like that, you can still use your old strategies, but L'Hopital's rule will work for any indeterminate form. So that's why it's so good. Now, before we start working on problems, I wanted to just do a quick reminder of some important limits. One thing I like to mention about these is that these are sort of like our basic limit properties, but you have a graphing utility available to you. So if you forget them, then you can absolutely use them just to remember. And just a quick reminder. So this first one here, it says, if you do the limit as x goes to infinity or negative infinity, it doesn't matter of a polynomial. Like the polynomial has to have at least degree 1, so there has to be at least an x in it. It can't just be a number. But let's say x raised to the 5th minus x raised to the 4th plus 3x minus 1. Minus 1. Then what this is saying is as we go to the left, so as we go to negative infinity, as we go to the right, positive infinity, whichever one you're doing, it's going to be an infinity. Right? And that's really useful when you're doing L'Hopital's rule, because if you have a fraction and you have a polynomial, you don't want to go through all the details of figuring that out, because whether it's infinity or negative infinity, it's not important which one it is. It's one of these forms, at least for part of your fraction, so you can just make a note of that. The other ones are revolving around e to the x. So the limit as x goes to infinity of e to the x is infinity. The limit as x goes to negative infinity of e to the x is 0. The limit as x goes to infinity of the natural log of x is infinity, and the limit as x goes to 0 from the right of the natural log of x is negative infinity. Now I wanted to remind you real quickly why we have to do the one-sided limit there is the domain of the natural log is only positive numbers, so you can't come at x equals 0 both ways. You can only come at it from the right. But you can see the y value, the graph gets so steep because the y value has a vertical asymptote. It goes down to negative infinity. And then the last little one here I have is if you're doing the limit as x goes to infinity of x raised to any power, if the power is positive, it's infinity. If the power is negative, it's 0. So like x raised to this fourth. As we go to the right forever, the y value is going to go up to infinity. But if it's negatives, it can be any negative number, 0.25, 24, whatever. As we go to the right, it's going to go, y value is going to go down to 0. Now this one really flattens out, so it might not look like it really gets there, but it will get there. Right. But that, I just wanted to give a quick reminder of these special limits because we're going to use them. There will be some other ones like trig ones that we'll use, but there's so many trig functions we can't possibly list them all down. And if we do need any reminder of them, we can just craft them. But outside of trig functions, this is pretty much the important limits that we're going to be making use of. All right, so the main thing we want to do in this section is just practice L'Hopital's rule. Right? There's not really necessarily any word problems that go with L'Hopital's rule. Really what doing a limit as x goes to infinity means, when we talked about that before, is in behavior. So if you do have a word problem, it's telling you what happens. Maybe x is representing time. As time goes on forever, you want to know what would happen to maybe your profit function as time goes to infinity if you're dealing with something, selling something, over time. All right, but a couple reminders here. When we evaluate the following limits, it is the L'Hopital's rule section. So we're pretty much going to be able to use L'Hopital's rule, but you want to make sure you can. Don't use it right away. Right? And remember the strategy for doing any limit is always plug in the number first. So if we hadn't talked about L'Hopital's rule, if we didn't have this new rule and I just gave you this section and told you do this limit, well, the first one is actually one you already know how to do. I want to show you that you can do it with L'Hopital's rule anyway, but you have to plug in the number first and understand that you're in the correct form. And then another thing, you might not use this often, but algebraic manipulation, so factoring, canceling, rationalization, if you have square roots, things like that, can still help you simplify first. And if you think about what L'Hopital's rule says, if you have a fraction, you're doing the derivative of the top and the bottom. If you can get rid of square roots or make it less at least, it's a lot easier than having to do the derivative with square roots, and you're going to have the chain rule, and it's already a fraction, so it's going to be even messier when you actually do the derivative of the top and the bottom. So don't forget about simplifying if you can. All right, but this first example, like I said, this is one that we could have done the old way and we've actually done before. This says the limit as x goes to infinity of x squared minus 4x plus 3 over x squared minus 8x plus 15. Now, one thing you might remember is that when you do the limit as x goes to infinity, if you have a rational function, which is a polynomial over a polynomial, if the top and bottom exponents are the same, then you just look at their leading coefficients and divide them. And this would be 1 over 1, which is 1. So just using that way, the old way, we could do this one much faster. But what I want to emphasize here is that we can still use L'Hopital's rule, and it can really be really the answer to any limit that's indeterminate form once you plug it in. But what we have to do is make sure that it actually is indeterminate form. Right? And the way we would do this is we would say, what's the limit of the top? So we can distribute the limit to the top. That's one of our limit rules. It's not a derivative rule, but it is a limit rule. We can do the limit of the top and bottom. And one of the things I wrote above is that the limit as you go to infinity of any polynomial is plus or minus infinity. So this is a polynomial, which means this is plus or minus infinity. I don't really care which one it is. And the same thing on the bottom. And we don't really know which one it is. It could be plus for both, minus for both. It could plus for one, minus for other. But the point is this limit, if we are just to plug it in, is plus or minus infinity over infinity. And the nice thing is that this is already of the form that we can use L'Hopital's rule. So this is in a form to use L'Hopital's rule. Okay. If it was not, so if we did have indeterminate form, which we'll see in the future, that's not already in the form, then one of the two forms, infinity over infinity or 0 over 0, we will have to manipulate it. But this one is. So what does it say? L'Hopital's rule says, well, take the original limit. I'm just going to rewrite it. And what I like to do when I do L'Hopital's rule is I like to just use L'(h) to say I'm going to do L'Hopital's rule. And what it says is we can do the derivative of the top. Well, this is actually what we want to do. The derivative of the bottom separately. So what's the derivative of the top? Well, the derivative of x squared is 2x minus the derivative of 4x is 4 plus the derivative of 3, which is 0. And then this is over the derivative of the bottom. So the derivative of x squared is 2x minus the derivative of 8x, which is 8, plus the derivative of 15, which is 0. All right, so what I just did in that step, I applied L'Hopital's rule because when I plugged it in, I had one of the indeterminate forms of L'Hopital's rule. And once again, L'Hopital's rule pretty much says do the derivative of the top and bottom separately. Right. But once I've done L'Hopital's rule, I can't just do it again. I need to now plug it in and see, do I get a number? Do I still get an indeterminate form? Well, let's just see. And if we go ahead and plug it in, we know that we really can't plug in infinity, but if we take the limit as x goes to infinity of the top, just kind of think about distributing it, the limit to the top and bottom like we did above. So the limit as x goes to infinity of 2x minus 4, that's infinity because this is a polynomial. Now it could be plus or minus, but it's a polynomial. And then the bottom, also a polynomial, so it's also plus or minus infinity. And this would be plus or minus infinity over infinity. All right, so what is this saying? This is saying do L'Hopital's rule again. Okay. All right. Now, in many examples, we might only have to do it once. In some examples, we might have to do it more than once, like this one. And then pretty much every other example will have to do L'Hopital's rule. We would not have been able to use an old way. But for this one, we want to go ahead and do L'Hopital's rule again. Keep in mind that after we did L'Hopital's rule the first time, we were evaluating this limit. So we do L'Hopital's rule again once we are in the simplified part after the first application of L'Hopital's rule. So we want to do the L'Hopital's rule on this thing. Now I'm going to go ahead and just kind of put this on the side here. We want to do the limit as x goes to infinity. I'm just going to rewrite it 2x minus 4, not plus 4, over 2x minus 8. And then I'm going to do L'Hopital's rule. So I'm just going to write above the equal sign L'(h). I just established in the previous part that I need to do it again. And this says we have a fraction. What's the derivative of the top? The derivative of 2x minus 4 is 2. And the derivative of 2x minus 8 is also 2. And 2 over 2 just equals 1. So this is the limit as x goes to infinity of 1. And the limit of a number is always just the number. We don't care if it's x to infinity or x to a finite number. It's always just 1. So this is 1. And that's exactly what we would have guessed or realized at the beginning because we could have used our old shortcut. Now, the purpose of doing an old problem is not to show you that you should do it this way. In fact, this old problem, we kind of realized the answer should be 1 in about 10 seconds. Doing L'Hopital's rule out, you have to do a lot of verification that you're allowed to do L'Hopital's rule. The point is, yes, you can use L'Hopital's rule for old problems, but you do want to try to make sure with the limits that we were doing back in chapter 2, or pretty much in the very first limit sections, that you want to make sure you're doing the problem in an efficient way. And this one, I would never actually use L'Hopital's rule if I was doing it on my own. But once again, just wanted to show you that it's possible. In the next video, we'll continue and we'll start looking at problems where we must use L'Hopital's rule. We won't have an old way to do it. I will see you there.